Hi students, this is Anusha, Assistant Professor, Department of Computer Science, St. Josephs College of Arts and Science for Women. So in this video we are going to see Congestion Control Algorithm Part 2 from the subject Computer Network. As we discussed earlier in the last video, congestion is nothing but congestion is traffic. So here we are going to see congestion control in virtual circuit subnet, congestion control in datagram subnet, load shielding and jitter control. Here we have two subnet, that is virtual subnet and datagram subnet. The first one is congestion control in virtual circuit. So here the subnet we are going to use here is admission control. One technique that widely used to keep congestion that has already started from getting worse is admission control. Don't open any new virtual circuit. Control opening the new path here. Once congestion has been signaled, no more virtual circuit are set up until the problem has been gone away. That is, don't open. Already it's full, so don't open a new circuit. An alternative approach is to allow new virtual circuit but carefully route all new virtual circuit around the problem. Open a new path, that is in another way. That is, you can select a different route. So in this diagram, there are two places where congestion has built up automatically. Automatically link has been broken because this particular link congestion occurs. Don't open a new path is our first condition. If you really want to open, then avoid those two congested paths. Open a different path, then there is no congestion, so there is no issues. So diagram B is redrawn subnet for removing the congested path from A to B where there is no congestion at all. Here we have two kind of admission control. One is don't allow the virtual circuit, or if traffic is high, find a new virtual connection. Next is congestion control in datagram subnet. Here the quality delay inside router directly captures any congestion experienced by packet. Maintain a good estimate of the queuing delay U. A sample of the queue length S can be periodically and U can be updated as U new equal to AU old plus 1 minus AF. New delay in queue A in A time, that old delay plus 1 minus A times the length of the queue. A is a constant value that determines how fast the router forgets recent history. That is EWMA. It is nothing but exponentially weighted moving average. Here the important thing we are going to see is warning bit. A special bit in the packet header is set by the router to warn source when congestion is detected. The bit is copied and piggyback on the acknowledgement and sent to the sender. The sender monitors the number of acknowledgement packet it receives the warning bit and adjusts its transmission rate accordingly. Next is choke packet. It is nothing but a more direct way of telling the source to slow down. A choke packet is a control packet generated at a congested node and transmitted to restrict traffic flow. The source on receiving the choke packet must reduce its transmission rate by a certain percentage. An example of choke packet is ICMP source pledge packet. It is nothing but Internet Control Message Protocol. Hop by hop choke packet. Over long distance, if your subnet is longer or at high speed, choke packet are not very effective. So here we use hop by hop method, an efficient method to send a choke packet is hop by hop or node by node. This requires each hop to reduce the transmission even before the choke packet arrives at the source. Router A to D packets are being sent. No issues. Think that router D reaches the maximum limit. Slowly congestion occurs. So immediately the router develops a choke packet, and this choke packet goes to the source first. So nothing is happening. Next is coming back. Nothing is happening. And again it is coming back. And in this place it reaches the sender. Now only source comes to know that it's being overloaded. This is explained in the diagram A, and in the diagram B, the choke packet is receives the sender A. Now choke reduces the flow as A reduces the load, still D is overloaded. Diagram A explains about a choke packet that affect only the source, and the diagram B tells that a choke packet that affect each hop it passes through. Next is load shedding. Shedding is dropping or shedding. When buffer becomes full, routers simply discard packets. Which packet is chosen to be with victim depends on the application and on the error strategy used in the data link layer. Which has to be thrown away? Which one has to be thrown away? For a file transfer, example, cannot discard older packet since this will cause a gap in the received data. For a real-time voice or video, it is probably better to throw old data and keep the new packets. So here the main concept we come across is random early detection. It is nothing but when the average queue length exceeds the threshold, the packets are picked up at random from the queue and discarded. The last topic is jitter control. It is nothing but the variation in the delay of received packets. Here, the differentiation within the latency between each data packet will be explained. For example, high jitter, that is nothing but some packet taking 20 milliseconds and other packets taking 30 milliseconds to arrive. It will give an uneven quality to the sound or movie. Low jitter. In contrast, an agreement that 99% of the packet be delivered with a delay in the range of 24.5 millisecond to 25.5 millisecond might be acceptable. So this is the diagram for the jitter control. Thank you.